Most of us learn the shape of the world from a classroom map. We see a planet divided into 7 distinct continents, separated by vast oceans. This photograph shows the Himalayas in Asia, a continent defined by high elevation, home to peaks that scrape the upper limits of the atmosphere. In Africa, sand replaces snow. Here you find the Sahara, an expanse of rolling dunes and the largest hot desert on Earth. Contrast that with South America. As seen in this aerial shot, the continent is dominated by dense rainforest woven around massive river systems. Then there is Antarctica. It is a frozen environment populated by penguins and massive icebergs, with no permanent human residence. These diverse landscapes form the foundation of our geography, yet focusing on surface appearances provides an oversimplified view of the planet. The definition of a continent depends on where you go to school. Students are taught that the world has anywhere from 4 to 7 continents. Take a look at this map of Europe and Asia. Geographically, they form a single, unbroken physical landmass. There is no ocean dividing them. The line that splits Eurasia exists because of cultural and historical identities that evolved differently on either side of the map. You see the same thing in the Western Hemisphere. In Latin America, North and South America are often taught as a single landmass called America. This cultural mapping extends to global symbols. This photograph of the Olympic flag features 5 rings representing the 5 inhabited continents participating in the Games. Consider this view of Greenland. It is massive enough to fit India's 10 largest states inside, yet it's classified as an island territory of Denmark. The borders we draw across the water and land are dictated by human perspective. To find the physical boundaries of the Earth, we have to look underneath the map. The inside of our planet Earth is built a lot like an onion, made of several distinct concentric layers. This diagram isolates those layers. At the center is a hot core. Surrounding that is the mantle, made of semi-solid viscous rock. Finally, wrapping the outside is a thin, solid outer shell called the crust. Geologists group the solid crust and the very top, stiff portion of the mantle together into a single layer called the lithosphere. This lithosphere is fractured into several massive, interlocking puzzle pieces known as tectonic plates. Because the mantle directly beneath them is semi-solid, these rigid rock plates constantly float, glide, and grind against one another. The jagged, hidden edges of these massive tectonic plates define the physical borders of our world. To see what this geological engine is capable of, we must rewind the clock hundreds of millions of years. This map shows the Earth as it looked in the deep past. Every landmass you know today was joined together into one enormous supercontinent called Pangaea, surrounded by a single global ocean. Eventually, tectonic plate movement caused Pangaea to tear apart. It split into a northern landmass called Laurasia and a southern mass called Gondwanaland. As the rock tore, ocean water rushed into the newly formed gap, creating the Tethys Sea. This entire geological process happened incredibly slowly. The continents drifted apart at roughly the same rate that your fingernails grow. Over millions of years, that microscopic daily movement added up. The continents we inhabit today are the drifting fragments of that single ancient supercontinent. Bring the timeline back to the present day, and the reality becomes clear. The shifting of the continents never stopped. This animation overlays our familiar political borders with the actual geological borders of the tectonic plates beneath them. When 2 of these plates collide head-on, the rock is forced upward. The towering peaks of the Himalayas are actively being crushed upward by this slow-motion collision. The process is often violent, as seen in this photograph of a ruined coastline. When tectonic plates snag and tear apart under the ocean, they displace water, triggering catastrophic earthquakes and tsunamis. The classroom map captures a single frame in a million-year-long geological movie.